the 0.05 significance level, does the data below show significant correlation? All right, so now to do this, we are going to need to look up a table, or look up in the table, the comparison value called the critical value to compare our correlation coefficient R. So this 0.05 significance level refers to the table that we use for looking up our critical values. Now we can look those up by going into our course, into the tests module, into test 1, and then click on the reference packet for test 1. The table is on the 3rd page, and as you can see at the top, it says 95% critical values. So that refers to a confidence level of 95% and a significance level of 0.05. So in this table with n-2 degrees of freedom, we can look up the critical value that we need to determine if our data has a strong enough linear correlation to use a linear model for predictions. So let's first find the critical value so we know where to set the bar. So we have how many values in our data set, how many pairs of data. We have 1, 2, 3, 4, 5, 6, 7, 8. Also notice that it's in row 9, the last set, and we do have a header, so 9 minus 1 would be 8. So our sample size, n, is 8. That means that our degrees of freedom, which is n minus 2, will be 6. So looking in our table here at the row for 6 degrees of freedom, we find our comparison value 0.707. So the critical value, 0.707. Now let's find the linear correlation coefficient for our data. We can use the Correl function, double click that. Notice that it wants array 1, comma, array 2. So just choose the first array, comma, the second array, enter. So notice that this is a very weak linear correlation compared to the critical value. We can also visualize this on a number line where we draw out, let's say we have this number line here representing our linear strength. So if the linear relationship is very, very weak or non-existent, it'll be a linear correlation coefficient of 0. But if it's very strong in the upward direction from left to right, then it would be perfect linear correlation at +1 and -1 on the other end if it was perfectly downhill. So this is our R number line, the linear correlation coefficient, 1, or you could think of it as 100% strength in the positive direction, meaning that it would be uphill from left to right, and -1 or 100% strength in the negative direction, downhill. Now we can look at a scatter plot. It's always good to do that, but since we were told to use a significance level, it means that we want to compare the value that we get out of the table. But just for curiosity's sake, I'm going to go ahead and make a scatter plot. And you can see that this does not appear to have a very strong linear correlation. And if you try to fit a trend line to it, notice that the trend line does not fit very well. Also, your R² value is pretty low too. So that's R if you square it, right? So if I take R to the power of 2, that would be this value raised to the power of 2. And if you change that to a percentage, you would say that the X values are only explaining about 4.75% of the changes in Y. So not a very useful model. Okay, this line here doesn't fit the data well. It has a very low R squared and a very low R value. Okay, so we're seeing all measurements pointing to saying that there is not sufficient linear correlation, and specifically because our critical value is at 0.707, which is somewhere down here, 0.707, our CV. Our test statistic is way back here, the test statistic R, and we would need our test statistic to meet or beat our critical value in order to say that there is enough linear correlation to use a linear model for making estimates. So the answer to this question is no.